Hello, and thank you for attending my presentation on MoP-CLIP, a mixture of prompt-tuned CLIP models for domain incremental learning. This work has been financed by MyTax through a collaboration between Thales and École de Technologie Supérieure, and has been a collaboration between José Dolz, Christian Desrosiers, Ola Ahmad, Imtiaz Ziko, Florent Chiaroni, and myself. In this work, we tackle the problem of domain incremental learning, which is a setting in which a model will be trained on multiple domains that will be seen sequentially. We will have access to one domain at a time, and afterwards, we will not be able to replay this domain. The aim of domain incremental learning method is to maximize the cumulative accuracy of the model through its lifetime. In other words, we want to make sure that the model consolidates its knowledge and does not forget, which is not straightforward with regular fine-tuning. Most domain incremental learning methods can be categorized between architectural strategies, regularization strategies, and rehearsal strategies. In this work, we use a novel strategy which is based on prompt tuning. We also try to introduce a novel and that we believe more realistic domain incremental learning setting. We empirically observe that state-of-the-art domain incremental learning methods suffer in the presence of out-of-domain data. And given the advantages of prompt learning applied to domain incremental learning and the limitation of state-of-the-art domain incremental learning methods, we propose a generalization of the state-of-the-art approach as prompts whose performance does not degrade under out-of-distribution data. As in the classical domain incremental learning setting, we will want to train a model sequentially, one domain at a time. But this time, during inference, we will also have the possibility to have samples from unseen domains whose test distribution is not aligned with any of the distributions that we saw during train time. It can be observed that most existing methods in literature are not robust in this setting. For example, if we train S-prompts, which is supposed to be the state of the art on domain incremental learning, on the 6 domains of domain net, we can see that the accuracy of classification on clip out is about 80%. But if we train this method on the 5 domains of domain net except clip out, its performance will degrade to 70% accuracy. In this work, we use prompt tuning to adapt large pre-trained models to new domains. Prompt tuning has multiple advantages over full model fine-tuning. For instance, we need less data to fine-tune the model to a new domain. We have faster convergence and less memory overhead for multiple downstream tasks. Indeed, for one pre-trained model, we can store very few parameters to adapt to multiple domains. In a classification model such as CLIP, we traditionally have one text encoder and one image encoder. The text encoder is fed with classes name and produces prototypes. The image encoder is fed an image and produces a feature representation, and the image will be classified according to the closest prototype. In prompt tuning, instead of feeding the class names embeddings and the image embeddings to the 2 different encoders, we also feed trainable weights as inputs. Those additional inputs, will be used to adapt the model to specific dataset. Our approach uses 2 steps to classify a given image. First, we add an additional step at train time, which we call domain representation. Indeed, we use clip image encoder to produce representation for each domain that we encounter at train time. And we produce class-wise prototype of the features of the images of each domain. Once we have one prototype per class per domain, We use these prototypes to compare the features that we obtain for a given image at inference time to decide if the image is inside those scene domains or not. We do this using the likelihood of the sample belonging to a known domain, which we model as a class-wise sample prototype modeled by a Gaussian. This model uses a likelihood threshold, which is an hyperparameter, which will be calibrated using ablation studies. If we compute that the sample is likely to be in domain, we will use a single model which is supposed to be optimal for this given domain. And if the sample is out of domain, we will use a non-sampling technique to generalize better to this new domain. If we compute that the sample is likely to be in domain, we will classify it using the model which was trained on the domain that is closest to the sample in feature space. If we compute that the sample is not likely to be in domain, we will use a non-sampling scheme to classify the sample. Indeed, we will ensemble the predictions of the different models that were trained on the different domains using Gaussian mixture model weights. That is, we model the new out-of-distribution domain as a Gaussian mixture of the domain that we encountered during training time. We benchmarked our approach using several datasets, such as DomainNet, which is comprised of 6 domains representing the same classes. We also benchmarked it using CDDB, which represents deepfakes generated with different deepfakes generators, and also Core 50, which represents different versions of the same classes across different domains. We used average accuracy at the final step as our main metric, and also cumulative accuracy of the model through these steps. We also represented the average forgetting of the model and the total forgetting to compute how much the model forgot and degraded while adapting. We offered a large improvement on unseen domains, and we did not degrade the performance on seen domains compared to SPROMs. This was seen on CDDB, but also on DomainNet and on Core 50. We carefully did an ablation study to study the different components of our approach on CDDB, which enabled us to select which distance to use in the case when we did not use any ensembling and when we did ensembling. We also showed that it was possible to improve the classification accuracy further if we had access to a validation set to tune the Q hyperparameter of the approach. To conclude, we identify an issue with existing domain incremental learning methods, which is that they suffer under distributional drift, and we propose a solution which is supposed to generalize better under distributional drift. This solution is exemplar-free and order-insensitive. So that's it. I would like to thank my co-authors and supervisors for this work. Thank you.